मैं करूँ? Hello and welcome. Today we are presenting the behavior of software laws for simulation of optoelectrothermal effect in large area devices. For example, AMOLED display, lighting panels, or PV module. There are various fields of application in which our software tool can be useful. We will share four main application and related simulation tasks in laws. The software allows you to understand the effect that occur on display, such as pixel crosstalk, and optimize the device design in order to achieve the best efficiency. By modifying the electrode layout parameter, here we focus on the lighting and display application of LAOs. OLED lighting panels should yield a homogeneous emission and keep the effect heat generation in order to achieve the prevent. Both can be achieved by optimizing the device design, for example, suitable material, metal grade design. In display, clearly defined such color with a good angular stability. This achieved by optimizing the pixel layout, their materials, and structure in between them. Laos is a simulation software that can address all those challenges. Laos consists of three different modules: electrical, thermal, and optical. All of them have their specific field of application. Let's start with the electrical module and thermal module of Laos. Before we show real application, we will so briefly explain the model and necessary input provided by the user. The electrothermal part of Laos is based on finite element method. On the two electrode, we solve the Ohm's law in two dimensions. They are coupled by a user-defined one-dimensional coupling law. Overall, this is a 2D plus 1D approach, mimic very well the three-dimensional nature of real application and is computationally much more efficient than full 3D treatment. Laos automatically run a meshing, solve the partial differential equation for the system. As an input, the user directly obtain electrical potential distribution, IB curve of device, and much more. You will first load the geometry. The top view of your device Laos will run an automatic meshing. Next, the user can define the further inputs such as coupling law, electrode conductivities. The simulation is ready to be run and the user can explore the results within a few seconds. One could now, for instance, modify the geometry and rerun the simulation cycle. Alternative to the free-form definition of geometry by DXF file. Laos offers few predefined geometry that can be readily used. Current will generate heat. This phenomena is well known as Joule heating. At a place with higher current density, one will measure higher temperature in order to simulate this effect. Laos offers the thermal module which has to be coupled. As a first and more simple option, there is only one way of coupling. Current will generate heat which will lead to increased temperature. The local temperature can also have a backward effect on the local current. This option is called full coupling and required to set a temperature dependent IV curve. When using the thermal module in Laos, the user can also have set some more parameter which define the different effect electrode or transfer the medium above and below the electrode. These are typically well known material parameter and can be looked up in literature. Let's now look at the application example that demonstrates the option of electrothermal simulation in Laos. The first example was inspired by experimental work by group of LG display company. They switched on all the blue pixel in AMOLED display. They observed that red pixel and lighting up, these turning the display purple. This understand effect is well known pixel crosstalk and occur in display which measures some common high conductive layer. The whole transport layer is shown in yellow. The key parameters are the pixel density and the layout and also material parameters such as electron doping density. We have used Laos in order to analyze and quantify this effect. In Laos, we load the pixel structure such as well as individual curve of red, green, blue pixel in order to mimic the experimental condition. We also switch on all the blue pixel by applying the same voltage to all of them. Laos directly calculate the potential distribution here shown 4 voltage applied to the blue pixel. Moreover, you can analyze the IV curve of the different pixel. Also, a non-negligible current in red and green pixel. This is called crosstalk effect that we wanted to simulate using current efficiency value. We can directly get the luminance value of different pixel. Up to 40% unintended emission from the red pixel compared to the blue pixel is observed. even if the effect decreases with high voltage. This will clearly hammer the color gamut of the final display. Next example, we look at OLED lighting panel. When you take a cursor, look at the panel and remove the scattering foil on top. You can see fine metal grid. This metal grid is necessary to achieve a uniform emission of the panel. One example such as metal grid has honeycomb-like structure shown on the right hand side. This grid is readily available in Laos as a predefined geometry. We are going to use this in the following example. Here on the left side, we show the simulated potential distribution without a metal grid. Clearly, the potential is non-uniform and drop the almost 5 volt in the center of the module. In order to achieve the increase the potential and consequently the luminance, a metal grid is used. On the right hand side, the potential is the center is only about zero point 0.2 volt lower than the outer edge. Such as panel without a metal grid and the corresponding luminance distribution has also been characterized experimentally. The Lao simulation agrees perfectly well with the major profile. The parameter of the honeycomb metal grid can be varied and optimized automatically in Laos. Here we show the potential distribution for a varied hexagon radius with decreasing radius. We clearly see a much more homogeneous potential distribution which would lead the improved uniform emission. However, metal grid is a non-transparent. It is also having some shading effect. This will increase with decreasing the radius and could lead to the lower emission in total. The simulation are now slow to find the optimal configuration of your electrode. Another effect that has been observed experimentally is the non-homogeneous surface temperature of OLED lighting panel because of the feedback from temperature to current. This will also result in non-uniform light emission. Here show some right hand side. We want to simulate this effect using the thermal coupling option in Laos. For simplicity, we can also simulate half of the earlier. You can see a clear that the temperature are the highest in the corner toward the center of the panel by about 40 degrees Celsius. One could also now easily play around with some parameter in the simulation to check how this deterministic effect could be decreased. The third module of Laos is the optical module. Again, we will start with the model, the input and output quantities. Laos optics is full 3D ray tracing algorithm which we use Monte Carlo method. The idea is fairly enough. Some rays are launched from a specific area. The pixel is marked with a yellow rectangle. We then follow the path of these rays throughout the stack which is defined by a specific layer and interface properties. Finally, we post-process information about these rays, for example, at which XY position they excite the top most interface. The stack and Laos optics is defined by a sequence of layer and interface. Layer and interface have specific properties which have to be defined by the user. The interface, for example, are defined by geometry or layout and topography. The geometry itself is further divided into subdomain. For example, 4 pixels shown here. Each of these subdomain are characterized by reflectance, transmittance, optionally emissive properties. There are several plots readily available in the result section of Laos. The polar plot reflects the far field intensity that could be seen by an observer looking at the device or detector that is used for characterization. The XY show all the rays that reflect last interface independent of their angle of incidence. The view can also be used to look at the microscopic scale. If a wavelength sweep is enabled, the Laos directly show the apparent color and output the color coordinate. A special feature is the CIE color diagram, which show the color point at the position of cursor. The trace of select ray are displayed in the sample ray plot, which help the user better understand the observed effect. The user can also inspect the 3D structure with a movable detector. Upon clicking the refresh button, the intensity on the detector area is displayed. Let's now move on to the application example generated Laos optics. The first example focus on optical pixel crosstalk. We implemented a similar structure such as presented by Lee at in Laos in order to mimic the full display. We simulate the smallest repeating unit and use periodic boundary condition. As an input, we have to provide the white OLED emission spectrum as well as the optical properties of the different color filter. Our initial settings are used as a reference structure in the simulation. We can now easily vary several parameters of display or the material used. For example, we can sweep the slope of pixel definition layer. Here we see the XY plot of intensity and color as a function of angle between the PDL and OLED pixel. The crosstalk can be seen predominantly at edge of neighboring pixel. The intensity map is used to quantify the light leakage as a OLED intensity of adjacent pixel divided by the intensity of the green pixel. Interestingly, the crosstalk is highest for a slope of 45 to 60 degree. Laos optics can also be used to inorganic lighting concept. Here, a panel from designed LED is simulated in Laos. The goal is to achieve a bright and homogeneous emission in a forward direction. In order to couple the light out of reflecting textured backplane is required. The structure of this backplane is now optimized using Laos optics. The reference structure without any texture is only emitting into the light above the upper hemisphere. The current solution is used in the application distribute the light much better. By further optimizing the backplane texture in Laos, even more uniform light emission can be obtained. As the last example for Laos optics, we will show the simulation of curved display. This display features inorganic OLED setting at one end that emit into the light guide. Also, homogeneous light emission in forward direction should be achieved by a specific texturing of a two curved interface. Different scattering structures have been tested in Laos, which lead to the potential distribution in emission, and optimized structure can be obtained from optical simulation without the need for time-consuming fabrication. So today we have shown you the potential distribution Laos simulation for lighting and display application. The three module and various examples have been presented to demonstrate the advantage of Laos